The performer model attention approximation has linear time and space complexity in the input token count, in contrast to vanilla transformers square complexity. So this is about the paper called Rethinking Attention with Performers. On my page I call this Performers Favor Faster Transformer Attention. It's basically about using this kernel approximation to approximate attention matrix, and this approximation of the attention matrix actually decomposes the attention matrix into two multiplications, and that speeds up this approximation. It uses this kernel approximation, which is something I've looked into before as I'm learning more about machine learning in one of the previous articles. That these blog posts that I published here. So this word movers embedding cheap WMD for documents. There's video there as well. So that was about using kernel approximations to approximate word movers distance, which is similar to the earth movers distance. So now here the same it has been used in transformer to reduce complexity from L squared, that means complexity of squared in the input token count, to linear. So how is this done specifically? So the attention mechanism is this kingpin of the transformer model. It drives the results, but also runs the memory and time record of input token count squared complexity in, as I mentioned, computation time and memory as well. And in the rest of the article, the D is a latent representation dimension, so it's sort of this embeddings dimension. The reformer and longformer and other models attempted to topple the complexity with L log L, but there was only one model, linformer, it was called, that had linear complexity, but it didn't achieve as good results as the performer that will be discussed here. It was recently published, and it achieves linear complexity, and in terms of the latent dimension, it's d squared log d, but the d is considered to be small. A big problem is actually the L, and that's what's being addressed. So how does it work? So we have this attention, which is a result of a calculation of some matrix multiplication and softmax. And the problem here is that the attention matrix is L times L, which causes a problem when you have to multiply it with the value matrix, which is L times D. And when you do this, you can see you have a L here and L here, so you have to do L times multiplication times L, so you get L squared. So if we could actually decompose the attention matrix into two matrices, some kind of Q prime, K prime, and we would multiply first the value matrix with the K prime matrix, and we would have this small dimension M here, then we would get complexity L linear in L and linear in M. And as a result, we would have M dimension here, and if we would do another multiplication here, we would add extra complexity, just another LMD. So we would be linear in L and linear in M, and if we make sure that the M is small enough, so we can approximate quickly with small enough internal dimension, we will reduce the complexity to linear in the input token count, in the sequence length. The sequence length is the problem.